And we're gonna go live on Facebook too. And we're gonna take a moment as attendees are starting to log in. Okay. All right. Let's see here. Okay, and are we working on Facebook? Oh, it looks like we actually are on Facebook. Okay, that's always great. Right. Right. Thanks to everyone who is logging in right now. This is Berkeley Public Library hosting Popping the Science Bubble. We're just taking a moment as folks are logging in tonight, and we are just so excited to bring you tonight's presentation. Right. All right. Okay. All right. So I think I'll get started with our introduction tonight, just as folks are logging in. All right. Thank you so much for everyone tuning in tonight on both Zoom and Facebook. Welcome to Popping the Science Bubble. This is a monthly seminar series that aims to share new research findings from grad students and postdocs at UC Berkeley with the general public and create constructive discussion about a variety of science topics. The program features 2 speakers at each seminar who will talk about their current research or a topic that they just find really interesting. The organizers are 3 graduate students at UC Berkeley, Jenna, Madison, and Oksana. And this is a longtime partnership with Berkeley Public Library, and we are just so thrilled to be hosting UC Berkeley grad and postdoc students, and we absolutely just love being able to host this program. The program is monthly on the 3rd Tuesday of the month at 5:30. If you are interested in keeping up to date with the seminars, we really encourage you to sign up for the Popping the Science Bubbles listserv. This listserv is the best way to hear about each topic of the month and to learn a little more about our speakers. And you can sign up for the listserv by going to Popping the Science Bubbles website. They have a WordPress, or going to our library's website, going to the calendar entry, which will take you to that website. If you're interested in watching past videos of the talks or tonight's talk, you can go to Popping the Science Bubbles YouTube channel, where our talks are archived. All right, so I'm going to pass this off to the Science Bubble team, and they're going to introduce tonight's speakers. Thank you so much.
Thank you, Kelsey. Hi, everyone. Thank you for being here. As Kelsey said, we are a group of graduate students at UC Berkeley hosting talks through or for our research community members, for the public, and we're excited to be here. We're here every month, 3rd Tuesday at 5:30, hosting a wide variety of talks that you can hear about either on our listserv or our website or Facebook or Twitter. There are a few ways to reach us. And after the talks, if any of these topics particularly strike your fancy, we'll also send out some cool resources where you can learn on your own or get a little bit deeper into the subject if any of these things kind of hit that curiosity spark for you. So as talk logistics go, we're happy to take questions during the talk. We'll be monitoring both the chat and the Q&A sections here on Zoom, as well as the comment section on the Facebook video in real time, so that you guys can ask questions about our speakers, as well as after each talk, hosting a few minutes of questions before the next talk, and also for a few minutes at the end of the hour. So we are happy for you guys to participate and ask questions about anything you are curious about, so please don't hesitate to join in. We're excited to be here and to have our speakers tonight, and I'll let Jenna introduce our first one.
Hey. So our first speaker is Dr. Chen, and she is a postdoc fellow at the University of California, Berkeley and the Lawrence Berkeley National Lab. She grew up in Beijing, China, and came to the US in 2012 for graduate school. Dr. Chen completed her PhD in cognition and neuroscience at the University of Texas at Dallas. She's a cognitive neuroscientist with expertise in advanced brain imaging and cognitive psychology. Her research explores how brain and behavioral challenges and changes in healthy and pathological aging. Outside of research, she enjoys traveling and playing with her dogs. And with that, let's welcome Dr. Chen.
I think you can see my slides. Hopefully it's working fine. Thank you very much for the nice introduction. I'm very honored and excited to talk about cognitive and brain aging today. A lot of times when we talk about aging, we think of the negative side of getting older. But today I want to talk more about aging gracefully from the perspective of a cognitive neuroscientist. So specifically more about cognitive aging and brain health. As most of us know, we live in an aging society. By 2034, there are actually going to be more older people than children in the US. So how to prepare as an individual and as a society has become a critical issue. And because we all know certain things can be quite challenging as we get older. For example, older people may become more forgetful and their memory becomes worse. Their speed when processing information may slow down, so they may not react as fast as young people. They may also become worse at multitasking. But at the same time, there are also things older people become better at, like knowledge, especially verbal knowledge and general knowledge about the world, because knowledge takes time to accumulate. And studies have also found that older people have better interpersonal skills because they may have met many different kinds of people, so they know how to best deal with challenging situations. And similarly, they may also be better at things that require experience. These are just some examples of changes that people may go through in aging. Some are negative, some are positive. Some may be more common than others. With all the examples, what I actually really want to say is this very well-known fact that thinking abilities change with age. And among all these changes, some appear to be declining with age, some are maintaining or even increasing. So now I'm going to show you a figure. This figure on the right is from a very classic aging study in 2002. It actually systematically examined thinking abilities in people across the lifespan from age 20. The scientists in this study invited hundreds of people to complete a variety of cognitive tests. These tests measured different kinds of thinking abilities, including speed of processing, or how fast your brain can respond to a stimulus, working memory, or how much information you can hold at the same time, long-term memory, and world knowledge. They then compared all the thinking abilities in people at different ages, and this figure shows what they found. Each line here represents one test score. Basically, from left to right, it shows the direction of the lines shows the trend of change from young to old. The higher the lines are, the better the performance. the cool color lines go down from left to right because these abilities decline with age. And that includes speed of processing, working memory, and long-term memory. But as what was surprising to researchers back then is that not all abilities decline with age. The warmer color lines actually go up because older people scored higher than younger people in world knowledge and verbal knowledge. This interesting finding has been replicated in many other research studies in different populations since then. Now scientists call those abilities that diminish and decrease with age fluid abilities, and those that accumulate and maintain throughout the lifespan crystallized abilities. And what's even more interesting is that when solving real-world problems that require both fluid and crystallized abilities, young people rely more on fluid abilities, while older people shift their reliance from the declining fluid abilities to their preserved crystallized abilities. And middle age is actually when people are able to utilize both very well. So that's one of the things I found really amazing about human brain or human cognition in general. That is, although we decline, we also adapt.
Hi, She. So we have a question. Oh, sorry. We have a question from the audience. So the question is, you mentioned that as people age, their ability to multitask decreases. Isn't there research that shows that the ability to multitask is significantly overrated across the spectrum?
So multitasking is a really complicated concept in general for cognitive abilities because it involves not just the working memory. That's one of the cognitive aspects I was talking about. So it also involves how fast you can basically manage doing cognitive tasks at the same time, and task switch from one task to another type of task. And it also involves inhibition. So it's a really complex concept. And because it's complex and it's essential for a lot of tasks, some of the abilities change with age more significantly than others. So I would say it is still one of the abilities that's vulnerable compared to especially crystallized abilities like verbal knowledge, semantic memory, those things that have accumulated throughout the lifespan. If that answers the question.
Okay, thanks. Yep, and you can always follow up with more questions. Yep.
Yes, please. I am terrible at monitoring the chat and the Q&A, but please feel free to stop me if you see any questions and any comments I should address.
Yes, no problem. We will monitor that for you. No need to worry about it.
Thank you. So all the cognitive changes I just talked about, they actually happen because there are structural and functional changes in the brain with increasing age. For example, as one gets older, our brain shrinks, like illustrated on this figure on the right. In aging, brain volume decreases as we see enlarged ventricles in the right brain. That is the empty space in the middle of the brain. And the cortex, that is the outer layer of our brain where most thinking processes happen, becomes thinner with age. The white matter, which is the lighter part inside the brain that supports communications across different regions in the brain, also starts to lose its integrity. At the same time, brain function also decreases. One example is that brain regions responsible for specific functions, like memory, may not respond as fast and efficiently as they used to. But at the same time, our brain is also adapting. For example, scientists have found evidence of compensatory brain activities. That is, older people may recruit additional regions that young people don't typically use. They do this to compensate for the decreased function I was just talking about. And brain may also reorganize with age. For example, regions that are not used to work together may start forming new functional connections, like building a new team as the old one becomes less united. And some people may be more adaptive than others. The balance between declining and adapting changes actually help us to maintain everyday function as we get older. So that brings us to the last part and the key part of aging, that is aging gracefully. I believe a lot of us have heard about all those stories where people just appear to be, some people appear to be resistant to any kind of age-related declines. They just don't age. This is actually one of the hottest topics in aging research as well, because we all want to know the secret to super aging. And what we actually know is that the individual difference in how one ages is huge. Although we can roughly estimate, based on research evidence and personal experience, how an 80-year-old person may be like, it is still very hard to guess one's age, even if we have all the information about their cognitive performance, because people at the same age can just perform very differently. One 80-year-old person may have very significant cognitive challenges, while another may perform as well as young people, or even better than young people. So the million-dollar question is why? Are there things we can do to slow down brain aging? Actually, yes, there are some known factors, especially modifiable factors, that may reduce the risk of developing severe cognitive problems. So I'm going to talk about the protective factors a little bit now. One very important key is maintain physical health, especially cardiovascular health, because it turns out to have a healthy brain, you need to have a healthy heart and healthy vessels that supply blood to your brain. So to maintain physical health, there are several things that include take regular exercise, avoid smoking, monitor your blood pressure and blood sugar, and eat a healthy diet. Another thing people didn't really recognize until recently is how critical good sleep is for brain health. Having enough and good quality sleep is very important for people's brain, because sleep plays like a housekeeping role that removes toxins in our brain that build up while we are awake. What's also important is mentally challenging yourself, like mental exercise. If you find your job not stimulating enough, maybe try to pick up a new hobby that you can learn and enjoy at the same time, because it will be good for your brain to develop all the compensatory activities and new connections I just talked about. And finally, social support is another very important factor, because having good friends and family is helpful, not just for your mental health, but it's also associated with better cognitive function and better brain maintenance in general. Well, I hope you have learned something helpful and useful today. Thank you very much for listening. I realize I went a little bit fast, but if you have any questions, I'm happy to answer anything you have and also explain anything further if I went too fast.
Thank you so much. We'll take a moment to see if we have questions here.
Yeah, and while we're waiting for if there are any questions to appear, would you like to share a little bit about what you do in the lab? Like that's like a little bit of your
Of course.
day-to-day lab life?
Yes, so I am a postdoc researcher. Part of my research interest, in addition to what I just talked about, is actually more focused on the pathological aging part. So basically looking at factors that may distinguish people who are on a normal aging trajectory versus those who are declining more significantly or at early stage of Alzheimer's disease. So we actually use advanced neuroimaging methods to basically visualize some certain types of proteins that lead to Alzheimer's disease in the brain in cognitively normal people. So it's basically at a very early stage before people actually develop symptoms, we try to detect those proteins and be able to see if there are early behavioral and brain changes that may predict if someone will eventually develop symptoms in the future. And that's also helpful for clinical trials to basically find a targeted population and also to monitor the clinical interventions.
Oh, wow. Thanks, yeah, for sharing a little bit about your research. That's really cool and very important. We have a couple of questions that came up in the Q&A and chat. I'll go to the Q&A first, and it's looping back actually to the multitasking question. So Gary asks, regarding multitasking, it seems that's different than context switching, which is also related. Does context switching decline as in fluid abilities?
I would say yes. So context switching, what in cognitive psychology we always say, or we often call it task switching. So basically the type of things you're doing is different from what you were doing. So it involves, of course, multitasking may rely on sort of abilities related to context switching, but it's slightly different conceptually. But yes, task switching or context switching does seem to change and decline with age. It's also like multitasking is also related to another concept that I mentioned briefly, that is inhibition. It turns out actually in aging, inhibition declines more significantly. So basically it tends to show that older adults often have a harder time to inhibit irrelevant information. And that may be related to sometimes they may be more basically vulnerable as victims of false information because they may have a harder time to reject false information and to inhibit those kind of distractions just cognitively in general.
Okay, yeah, thanks for sharing that. And I guess when you were saying that too, I was also thinking about like how scammers target like older people too. And I guess that's kind of preying upon that aspect you were talking about.
Yeah.
Okay, so another question is there a way to recover from brain damage, like from radiation or chemotherapy or cancer treatment? Such as from symptoms of like brain fatigue and microglial inflammation?
That's a good question. I would say brain in general is flexible to some extent. There are like new wires, new connections that can build up after like certain age or a certain like operations or like treatments. But I'm actually not a clinician, so I don't know specifically how those can happen. And I don't really work with like patient population very much, but I would say brain is in general amazing, and the plasticity is great. So this is also one of the fields that a lot of people are still studying and exploring. So I would say it's possible, but I don't know like the mechanisms underlying the phenomenon. But in general, brain is really like capable of developing new wires connections in general, although it's not as easy as when we are young and developing, growing as like children. But basically the brain itself it still has the plasticity.
Okay, yeah, thank you for sharing that. Even though it's like, yeah, you don't do clinical research, but yeah, brain plasticity probably underlies a lot of questions and solutions for healing the body. Okay, so if we don't have any more questions at this time, feel free to like just type any questions in the chat if they come up later on, and she will be able to answer them in the chat themselves. But for now, we'll move on to the next talk. Let's thank Dr. Chen again.
Thank you.
Our second speaker tonight is Natasha, who is a first-year PhD student in the astronomy department at UC Berkeley, studying black hole and binary microlensing. She completed her undergraduate degree at Harvard University in 2021, where she joined concentrated in astrophysics and physics. She grew up in New Jersey, just outside New York, and enjoys singing, board games, and reading fantasy books. We're very excited for your talk. Take it away.
Thanks so much for that intro. So I'll be talking about black holes today, which I think are the most fascinating zoo in the universe, since we'll be talking about all sorts of different kinds of black holes and how we find them. So first, what is a black hole? So it's a point of immense density that's so massive that not even light can escape from its gravitational pull, hence why it appears dark. It curves space-time around it, as described by general relativity, which changes the orbits of things nearby it, including objects with mass, like other stars or things like this, but also actual photons. It actually bends light around it. So the anatomy of a black hole is that in the center, you have a singularity, which is this point of infinite density. And then outside of it, the exact radius of which is determined by the mass of the black hole, is the event horizon. So outside of the event horizon, things can still escape. You can have a certain escape velocity that will let you get away. So the same way that if you're on Earth and you throw a ball up, it's going to come down because there's gravity pulling it down. But if you're moving fast enough, like in a rocket, you can escape. Inside of the event horizon, though, not even light can escape. Light's moving, the light has the fastest speed that is possible in the universe, the so-called speed of light. And inside the event horizon, not even light can move fast enough to escape, hence why the black hole appears dark. So first, I'll be talking about astrophysical black holes. We think that these are remnants from exploding dead stars. And these are going to be on the order of the mass of our sun, between a few times the mass of our sun to about 100 times the mass of the sun. So how do we detect these stellar mass black holes? So there's a few different ways. One of them is by looking at X-ray binaries. So a binary is when two objects are orbiting around each other. So a star and a star and a black hole, or two black holes. In the case of an X-ray binary, you have a very massive and large in radius giant star and a black hole. So in this artist's depiction on the right, this blue is the star, and it's so large in terms of its radius that the outer layers, it can't actually hold on to them quite well. It's actually going to be a little puffed out, and the black hole can actually pull material off of it to accrete onto the black hole. So that's what you can see here happening. The material is pulling off of the star onto this black hole. So here is the accretion disk. And so that actually glows. And so for the same reason that if you rub your hands together, they start to get warm, or if you rub sticks together, they start a fire. Here, the gas rubs together and you end up with it glowing. And if you look for the particular patterns in how that black hole accretion disk is going to glow, we can actually figure out by looking in the X-rays that we are looking at this X-ray binary type system, and we can figure out the mass of the black hole. And so we found about 20, between 3 and 23 times the mass of our sun. We found about 20 black holes. We can also look for black holes via gravitational lensing. So that is when, as I mentioned earlier, black holes bend space-time, which bends light, and so do other objects. So in this depiction here, so we have some massive object like a galaxy in a cluster bending light around it, and the light from some distant object is bent around it and creates these distorted images of that distant object that we can actually see. And so if we're looking into the page over here, or into the screen, this galaxy here is acting as the lens, and then behind it is a blue galaxy, a spiral galaxy that's like our Milky Way, that's being bent around it. And we see this distorted image as all sorts of light rays that otherwise wouldn't have reached us are being bent around this distorted image into our eyes. And you don't actually need to have any light as a lens in order to have gravitational influence. And so, yeah, you don't need any light to have any gravitational influence. And so it's a great way to look for dark objects like black holes. So in the case of black holes, though, you're going to have something called microlensing. And so these objects are moving with respect to each other in our galaxy. So black holes and stars, they all move. And another thing is that we're not actually going to be able to make out those distorted images. They're too small for our telescopes to see. So instead, we're just going to see an increase and a decrease in brightness as those images come into existence and leave as the objects move with respect to each other. So in this animation over here, in yellow, we have the lens. In red, we have the source moving by. And in blue, we have these lensed images of the source. And as I mentioned, we're not actually able to resolve those lens images. So instead, we just get this, here's this magnification as a function of time. We get this increase and decrease in brightness. And so this is a really powerful technique because it can be used to find isolated black holes. All the other techniques that I'll talk about for astrophysical black holes, you need a binary companion for it to interact with. But we expect there to be plenty of black holes that aren't in any sort of binary. And so the way that we look for them is by looking for long duration events. Since black holes curve the space-time or any massive object will curve the space-time around it in a larger area, the event will last longer, even if the black hole is moving is moving quickly. So we can also look for gravitational waves from mergers. And so, as I mentioned, there are many black holes that are in binaries. And so if the two objects are close enough to each other, they'll lose energy and start spiraling in towards each other, emitting gravitational waves. So in this artist depiction on the right, we have these two black holes spiraling in and these ripples of space-time that are being emitted as they get closer and closer and will eventually merge. And so LIGO, the Laser Interferometric Gravitational Wave Observatory, has actually measured a number of these stretching and squishings of space-time by having these really long lasers that they can see little changes in after the space has literally been stretched and squished. And so they found a number of black holes. So this graph, you can read it as this is mass with bigger masses up here, smaller masses down here. And this is just like the order that they found the events in, no particular measurement. And so you have these two black holes, these two blue dots that come together to make this larger black hole, this more massive black hole. And as you can see, we have found plenty of these events with black holes as small as about 3 times the mass of our sun to as massive as nearly 200 times the mass of our sun, which is pretty cool. So I've talked about a lot of astrophysical black holes. So these are between 3 and 100 times the mass of our sun. And I will shortly talk about black holes that are so-called supermassive black holes that are about 100,000 times or more the mass of our sun. But between them, there aren't actually any black holes that we've ever found. We would think that we would find them because we think that black holes grow by accreting mass, like sucking in this mass from stars and gas, or by merging with each other to form larger black holes. And we see these really massive black holes. So we would think that we would be able to see them along the way, getting bigger and bigger. But we haven't found them, so it's an open question. So now I'll talk about these supermassive black holes that I just alluded to, that are 100,000 times the mass of our sun or more. So we think that there's a black hole at the center of our galaxy. So here's a representation of the Milky Way. This isn't actually a photo. We don't actually have a camera outside of our galaxy. We're inside of it. So we made this reconstruction. And we think that there's this black hole in the middle here. And we think so because we've mapped out the orbits of individual stars that are really close to the center of the galaxy. So the name of our black hole is Sagittarius A star. And you can see in this movie, the individual orbits of stars. So this is done with the Keck telescope in Hawaii this is animation is the UCLA Galactic Center group. And as you can see, all of these stars are orbiting around this white star in the center of the image. By mapping out the orbital mechanics, we've actually found that the object in the middle needs to be 4 million times the mass of our sun. But we don't actually see anything there. We just see them all moving around this point. And so we think that this is a black hole. And Andrea Getz and Reinhard Getzel got the Nobel Prize for this in 2020. So another way we've directly observed black holes is the so-called picture of a black hole from the Event Horizon Telescope. And it's in the M87 galaxy. And it's about 6 billion times the mass of our sun. So it's very, very massive. And you might ask while looking at this, okay, what is this glowing thing? Why is there, I guess maybe this is a black hole. So this is a simulation from NASA. So this glowing part is actually the accretion disk. As I mentioned before, that gas is moving around, rubbing together, glowing hot. And so it is flat. So you might ask, well, why is there this upper part and this lower part? And that's because of gravitational lensing. So we have this flat accretion disk, but there's a black hole in the way and it's bending the light around it. And so we can see the front part, but we can also see these upper and lower part. In the middle here is the inside the event horizon. So light isn't able to escape. The so-called black hole shadow, where light isn't able to get out and it looks dark. And here, this sharp part is the so-called photon ring, which is the innermost stable orbit of the photons. So if we go back, you can see this bright donut structure around the center of the black hole, or around the center of the black hole shadow. You can't actually see the photon ring since the resolution isn't that good. But it's still pretty amazing. So when we took this picture, it wasn't an actual picture, the same way that you might think for some of these other pictures. Instead, we used, radio very long baseline interferometry. So here's a map of the Earth with a bunch of telescopes on it. And so these are telescopes that observe in the radio waves. And you can correlate the different images that these all take to create this kind of simulated telescopes as the size of the Earth. And you can infer what's in between, which decreases your resolution, but you're still able to, or rather, it makes your image look more fuzzy, but you can look, you can get very good resolution. So finally, I'm going to talk about quasars. So we think that there are black holes at the center of all, or most if not all, galaxies. And so some of these have these very brightly shining objects, that some of which have these powerful jets that shine 1,000 times brighter than the entire Milky Way. So the way that this works is that, well, you still have this accretion disk of this material getting sucked into the black hole. But we also think that these black holes have very powerful magnetic jets that stir up the material and shoot them out in jets. And so these are some of the brightest objects in the universe. They are so bright that they look like pinpoints of light. And quasars comes from quasi-stellar objects because people thought that these were actually stars. But when they found out how far away they were, they figured that they must be in external galaxies. And so monitoring these, we can figure out the masses and various qualities of these black holes. And they're often in gas-rich galaxies where they can guzzle up tons of material and shoot it out. So in summary, black holes are these bodies of immense density, such that light cannot escape their gravitational pull. Black holes less than about 100 times the mass of our sun come from the explosions of stars. They're the dead remnants. We can detect them via X-ray binaries, microlensing, and gravitational waves. And these, among other ways. And supermassive black holes are greater than about 100,000 times the mass of our sun. And we can detect them via stellar motion, radio interferometry, quasars, among others as well. Thank you. Any questions?
Great, thank you so much. That was just a great presentation.
Yeah, great. While questions come trickling in, I have one that is probably pretty naive, but I know nothing about this field to kick us off. Is there a limit to how many black holes could possibly exist in our universe, or like a limit in their density? I recognize the universe is infinite, so like what percentage of infinite could you have maybe is a difficult question to answer, but
yeah, so that's a really interesting question. So we don't know because, so you may have heard of this concept of dark matter, which I didn't touch upon it here at all. But if we measure the masses of like galaxy clusters or even our own galaxy, we notice that there's a lot of missing mass. And some people think that it actually might be black holes that could explain that missing mass. So those are often called primordial black holes, or originally they were called machos, these massive compact halo objects. That was the name for the ones that were in our own galactic halo. There were various experiments that were done in our own galaxy, actually via microlensing, looking out at neighboring galaxies and seeing if any halo objects could pass in front of these external ones. And they found that they only found enough microlensing events to explain like up to about 10% of the halo being due to machos. But theoretically, maybe there's like still like it's possible that there are like very, very small black holes that we missed, or like very, very large ones, or they clump weirdly. So in a world where dark matter was explained by black holes, that could be, it could be like 30% of the universe's energy density. Probably is not that much, but that's probably the upper limit.
cool, thank you.
Sure.
I have a question about quasars, I guess. Yeah. Sorry if I misunderstood it, but I guess because I was looking at that image. So is it like, are they shooting out of the black hole itself?
Yeah,
Okay,
exactly.
so yeah, I guess I'm thinking of them as little geysers, kind of like Old Faithful in Yellowstone. I don't know if that's a good analogy, but I guess as a follow-up to that visualization, how can they be shooting out of the black hole if the black hole I thought was supposed to like suck everything in?
Yeah, exactly. So if we go back all the way to this, anatomy of a black hole. So inside the event horizon, nothing can escape. That's why, like, we see the darkness in the like event horizon telescope image, among other things. But we think that the material doesn't actually go in there yet. Like, you can still escape if you're moving fast enough, as long as you're far enough away. So you can, like, get kind of close and then be shut out so nothing is coming out of the actual event horizon. But like, these things are like massive. If you see a picture of a galaxy, I should have maybe put one in, but like, we actually have like images of these jets where it's like a galaxy's this big and the jet like goes all the way out here. It's pretty awesome.
Okay, wow, thank you for explaining that.
Sure.
Okay, I'm not sure if too many other questions. Oh, one's popped up on the Q&A. Okay. We have a question that's asking, do the quasar jets steal energy from the black hole?
So I guess depending on what you mean by steal, sure. So like, yeah, material that otherwise would have increased the mass of the black hole, like, is being shot out. But there's always, in any process, there's going to be some sort of like efficiency factor, and black holes are some of the most like efficient objects in the universe that we know of, but they're like efficiency of like transferring like mass to, or like matter to like mass energy is still only about 10%. So the black hole is probably not going to get that much bigger anyway. Yeah.
Great, thank you. And then I just wanted to ask, like, you as a personal question, what do you think is like the most like interesting confounding puzzle currently about black holes? What's your favorite thing to wonder about when thinking of black holes?
Yeah, so an interesting question that I did not actually really talk about here, but is kind of relevant. So in this plot, there is so I kind of obscured this, but here, so these orange dots are actually neutron stars, which are very dense objects, but they still emit light. And they're kind of like, when the stars explode, if the core is massive enough, it'll become a black hole, but not quite, it might become a neutron star. And so there is an upper limit to those masses from like statistical mechanics, but then for a while we had this like kind of lower mass black hole mass gap between mass where neutron stars are, and for a while we had only really seen its X-ray binaries, and they were only like 3 or 5 times the mass of our sun. And so there was this gap between, we thought, the upper limit of the neutron stars and the lower limit of all the black holes we found. And so but now, like, we're finding, so we thought that there was this gap, and now we're finding a lot of black holes in this gap, and it's like, well, why are all of these different methods kind of giving us different pictures of where the gaps are? There's also like this phenomenon called pair instability supernova that should put an upper limit on like masses of like black holes from stars, but we're also finding black holes from up there and via LIGO. So basically, like, why do we think there were gaps there in the first place? And why are we now finding black holes that we thought were in these gaps? And then why are there still gaps that we are confused about why they exist? Yeah.
Sounds interesting. Definitely a little bit out of my field, but sounds
Yeah, sorry
like
if I wasn't
something.
super clear.
If you can find evidence for it, why do you think it shouldn't be there?
Yeah.
Why do you still model that it shouldn't be there if there's evidence for it? Those are always
Yeah, or it's also like,
fun ones.
you know, it's like, okay, then why did this method find them, but then this method didn't? You know, all these questions.
Cool.
Yeah.
Okay. Well, I think unless anything comes in super late, there aren't currently any audience questions, but if either of these topics, or hopefully both of these topics, have spurred any curiosity in this sort of science, we will send out a post-seminar email with resources related to both of these topics. So we're always happy, or we will support you learning more. And then, of course, we're always happy to be contacted after the fact and take any extra questions. Oh, but we do have one last minute question for Natasha, asking, is there a way to predict whether a star will become a neutron star or a black hole or whatever else exists? What about the density of our own sun? Like, what would that predict? I think is how the second part of that question.
Yeah, so you can get a very good sense from the like the initial mass of the star, what the fate is going to be. Of course, there's some like nuances that like end up explaining what's happening exactly on the boundary. But for our own sun, it's actually never going to explode. It's not going to become either a neutron star or a black hole. It's not really massive enough to get to that point. What's going to happen to our sun is that it's going, so in the center of our sun, the reason it shines, and the reason why any star shines, is that it's doing nuclear fusion. So like it's merging hydrogen atoms together to make helium. That's still what it's doing, but beyond that, it'll start to merge helium atoms together and so on and so forth. Stars that explode need to be so hot that they can keep fusing elements together all the way till they get to iron. And then when iron happens, then the energy that's released from fusing iron isn't enough to hold up the gravitational, isn't enough to fight against the gravity of the star collapsing in on itself. And so that's when it explodes and you get a neutron star, a black hole, something like this. For our sun, it's not going to get there. It'll get to maybe carbon or oxygen. And by get to, I mean like just increasing number on the periodic table. And so at around that time, it's going to kind of poof off its outer layers into what's called the planetary nebula. You may have seen pictures of the Crab Nebula or all sorts of these really beautiful objects. And inside, you're going to have this little white dwarf. It's really brightly shining object, but it's not fusing. It's bright for other reasons. Yeah.
All right, and I think on that note, we want to thank both of our speakers for being here tonight. There were two really cool talks, luckily into different areas, so we got to learn about a bunch of fun different things. So thank you very much for being here with us tonight and teaching us about all sorts of science.
Yeah, thank you so much. These were just fantastic talks. Thank you so much, Science Bubble team. And we will be back next month, third Tuesday of the month at 5:30 p.m. All right.